In statistical testing, we are often interested in testing a hypothesis about the population average. So, for instance, we might be interested in the null hypothesis that the average wages in the economy are equal to £27,600 per annum, against an alternative that the average wages are not equal to 27,600. Now, we know that if we have n independent and identically distributed observations of y, then if those are randomly drawn from the population, then the sample mean, y bar, is an unbiased estimator of the population average. So in other words, on average, it would produce the correct value. We also know that if we have a large enough sample, that the sample mean will be approximately normally distributed with expectation equal to the expectation of y and variance equal to the variance of y over n. Now, in order to standardize a sample mean, we need to know what this sigma squared y is. And in reality, we will rarely know what the true variance of y is. So we're going to need to try and estimate sigma squared y. In this video, we're going to try and derive an unbiased estimator for the variance of a random variable. To do this, let's begin with a random variable. We've got a random variable x with expectation mu x and variance sigma squared x, and we take n independent and identically distributed observations randomly sampled from the population such that the expectation of each of those observations is equal to mu x and the variance is equal to sigma squared x. Now we know that the variance of x is equal to the expectation of the square of x minus e of x. We also know that the sample mean is an unbiased estimator of the expected value of x, and we've got two expectations here. So this gives rise to a suggested estimator for sigma squared as sigma hat squared is equal to 1 over n times by the sum from I is equal to 1 to n of xi minus x bar squared. And the reason that this is a suggested estimator is we know that the sample mean, x bar, is an unbiased estimator of the expected value of x. We also know that the sample mean is constructed by adding up all of the observations and dividing by n, and that's effectively equivalent to thinking about this as being a bit like an estimator for this expectation. Now, what we're going to try and do is we're going to try and analyze this estimator to see if this is an unbiased estimator. And remember, this sigma hat squared, it will be an unbiased estimator of the population variance sigma squared x if the expected value of sigma hat squared is equal to the true population variance sigma squared x. Before we start analysing this estimator, we're going to need to construct some identities that we'll use later on. Now, we know that the variance of x, which we can denote as sigma squared x, is also equal to the expected value of x squared minus the expected value of x all squared. Now, from before, we know that we can denote e of x as mu x squared, so we could rewrite this expression to give us that sigma squared x is equal to the expected value of x squared minus mu x squared, and that allows us to rearrange for the expected value of x squared as being equal to sigma squared x plus mu x squared. That's the first identity that we're going to use later in our proof. We also know that the variance of the sample mean, if the observations are IID, is equal to the sigma squared x divided by the number of observations. So the variance of the sample mean is equal to the variance of x divided by n, but we could also write the variance of x bar as being equal to the expected value of x bar squared minus the expected value of x bar all squared. And all that we've done here is we've written the variance formula in terms of x bars. We've got the variance of x bar is equal to the expectation of x bar squared minus the expectation of x bar all squared. Now we know that if the observations are randomly sampled from the population and are independent identity distributed, then this expectation of x bar is equal to the expectation of x. And so this whole expectation of x bar squared will be mu x squared. We know that the variance of x bar is equal to sigma squared x over n. So we can rewrite this expression to give us that the expected value of x bar squared is equal to sigma squared x over n plus mu x squared. We will use these identities again later in this proof. Now we want to analyse our estimator sigma hat squared, and we're going to want to take expectations of this in order to analyse whether this is equal to the true population variance of x or not. Now, these sorts of estimators are always quite difficult to deal with because we've got a squared term inside the summation. And a good place to start is to multiply out the brackets so that we can simplify our expression. So we can rewrite this as being equal to 1 over n times by the sum from I is equal to 1 to n of xi squared minus 2 lots of xi x bar plus x bar squared. So all we've done there is we've multiplied out this xi minus x bar squared term to give us xi squared minus 2xi x bar plus x bar squared. Even having squared our brackets, this is still quite difficult to deal with, so let's try and split this up into 3 terms relating to 3 separate summations. So we can write this as being 1 over n times by the sum of the x squareds minus 2 times by the sum of the xi x bars plus the sum of the x bar squareds. Now there's a few things that we can do straight away. X bar is effectively a constant within this summation, so we can take it outside the summation. We also know that x bar squared will be effectively a constant, so we can turn this term into n lots of x bar squared. So we can rewrite this expression as being equal to 1 over n times by the sum of the xi squareds minus 2 times by x bar times by the sum of the xi's plus n lots of x bar squared. By definition, the sample mean is just equal to 1 over n times by the sum from I is equal to 1 to n of xi. So that means that if we multiply left and right by n lots of x bar is just equal to the sum from I is equal to 1 to n of xi. So we have a sum from I is equal to 1 to n of xi within the brackets. So we can replace this with n lots of x bar. So rewriting the expression gives us that this is equal to 1 over n times by the sum from I is equal to 1 to n of xi squared minus 2 times by x bar times by the sum of the xi's, but remember the sum of the xi's are n lots of x bar plus n lots of x bar squared. Now what we've got is 2 times by x bar times by x bar times by n, but that's the same as 2 times by x bar squared times by n. So we could rewrite this a little more to give us 1 over n times by the sum from I is equal to 1 to n of xi squared minus 2 lots of n x bar squared plus n lots of x bar squared. And we can cancel out one of the sets of nx bar squared, giving us that this summation is 1 over n times by the sum from I is equal to 1 to n of xi squared minus n lots of x bar squared. So we've shown that our estimator can be rewritten as 1 over n times by the sum of the xi squared minus n lots of x bar squared. Now if this is an unbiased estimator, then remember the expectation of this sigma hat squared would be equal to the true population variance. So we're going to need to take expectations of our sigma hat squared, which is going to be the same as the expectation of 1 over n times by the sum from I is equal to 1 to n of xi squared minus n lots of x bar squared. Now, we're taking the expectation of a product, and we know that the expectation of any constant times by a random variable is that constant times by the expectation. So we can take this 1 over n outside of our expectation, giving us that this is equal to 1 over n times by the expectation of the sum from I is equal to 1 to n of xi squared minus n lots of x bar squared. We also know that the expectation of any sum is equal to the sum of the expectations, so we can take this expectation inside the summation sign. We'll also be taking the expectation of n x bar squared, so we can rewrite this as being equal to 1 over n times by the sum from I is equal to 1 to n of the expectation of xi squared minus n lots of the expectation of x bar squared. Now, we know that the observations are independent and identically distributed, and they're randomly drawn from the same population. So this expectation of xi squared will just be equal to the expectation of x squared for all observations. So we can replace this expectation of xi squared with the expectation of x squared, and that's a constant within a summation, so that'll be expectation of x squared plus expectation of x squared n times. So we can rewrite this as being equal to 1 over n times by n lots of the expectation of x squared minus n lots of the expectation of x bar squared, and we have n multiplying here, we've got n multiplying here, and we're dividing the whole expression by n, so the n's are going to cancel out. So that n, and that n all cancel out, giving us that our estimator is equal to the expectation of x squared minus the expectation of x bar squared. Now, from this point, we can use the identities that we constructed earlier. We know that the expectation of x squared is equal to mu x squared plus sigma squared x. We know that the expectation of x bar squared is equal to mu x squared plus sigma squared x over n. So this whole expression is going to be equal to mu x squared plus sigma squared x minus mu x squared minus sigma squared x over n, which is equal to the mu x squared terms cancel, so we'll have sigma squared x times by 1 minus 1 over n, or this is equal to sigma squared x times by n minus 1 over n. Now that is not equal to the true variance of x. So we've shown that our estimator sigma hat squared, which remember is equal to 1 over n times by the sum from I is equal to 1 to n of xi minus x bar squared, we've shown that that is a biased estimator of the variance of x.